Thank you very much. Okay, so before I dive back in and release the suspense from yesterday morning, where I said we're going to talk about what cyclotomic spectra actually are, I have a few comments on the last lecture. So there was this business about all of a sudden I didn't know what two things I was comparing when I was talking about agreement. So there was a step missing in the process of associating, starting with the DG category, and then I was getting from that a simplicial DG category. And then what one has to do, in fact, is like collapse everything and take the direct sum over all pairs of objects, and you look at all of these morphism spaces, and that gives you a big chain complex. And it's the homology of that that's actually equivalent. So it's like there was one more sort of collapsing step that was missing in that explanation. So what we were doing yesterday, what I spent a lot of time talking about with Brave New Algebra, is that I talked about model structures that we had on categories of orthogonal spectra. That's sort of our base category when we were doing stable homotopy theory. And then for any finite group G, we moved on to orthogonal G spectra, which were orthogonal spectra with a G action. And the big difference was how we were going about defining equivalences of these. So I just defined a notion of equivalence for orthogonal spectra. And then we had a notion of equivalence on orthogonal G spectra that involved these G fixed points. And we wanted to have induced equivalences on all of the fixed points with respect to different subgroups of whatever group you're talking about. And at the very end, I was talking about orthogonal T spectra, where T is the circle group. And then we said, well, what we're going to do is we want to have equivalences with respect to all of the finite cyclic subgroups. So now that we have all that put together, I can introduce the category of orthogonal cyclotomic spectra. So definition. We're going to talk about the category of orthogonal cyclotomic spectra. Orthogonal cyclotomic spectra. So what are the objects in this category? So it's going to consist of, to start with, a T spectrum. So it's going to be a pair of things. It's going to be an orthogonal T spectrum, and then a bunch of maps. Okay, so our X now, if I found the right way to write this, is an orthogonal T spectrum. And what are these maps phi n? Phi n is going to be a stable equivalence from, or an S. I'll get there. We take the Cn fixed points of X, geometric fixed points, and have a map from the Cn geometric fixed points of X to X that should be now a T equivariant map. And this is in a map of orthogonal T spectra, and this should be one of these F equivalences that we were talking about last time. So we see this one is a T spectrum because if you look at T modulo Cn, it's still going to be isomorphic to T. So that's why this makes sense to think of this as a map of T spectra, and this should be one of these F equivalences, so that if we look at the restriction to any finite cyclic group, it should be an equivalence of equivariant spectra as we defined yesterday. Moreover, so just move this up. Such that there should be compatibility among all of these sort of structure maps. And it looks like this. So if I look at, if I take my spectrum, I take its Cm fixed points, and then I again look at that as a T spectrum, and then I take the Cn fixed points, then here I can take phi Cn applied to phi m, which gives me a map here. And then I could take phi n, which gives me a map to X. Or I could recognize that because of the way geometric fixed points work, this is actually the same thing as phi of Cn plus m. And then this would be phi n plus m, and this thing should commute. And that for all m and n. So they have to be compatible, all these different structure maps in this way. Now, one comment I would like to make here is that there was a reason why I talked about free loop spaces yesterday, and the fact that if you look at a free loop space and you look at its Cn fixed points for some n, then this is actually homeomorphic to your free loop space. So this kind of structure that we're seeing here is that kind of thing where the geometric fixed points are playing the role that the ordinary fixed points played on the free loop space. So it's a similar kind of structure that we're seeing here. Oh, sorry. I should actually read my notes. Thank you. Of course. Right. So we get this. And then we're going to say that a map of cyclotomic spectra, so if I have an F, which is a morphism of cyclotomic spectra between two pairs like this, that this one is an F equivalence if on the underlying T spectra, it's an F equivalence. Is an F equivalence, if it is so, just on the underlying T spectra. So you don't need any other further conditions. OK. So that's what yes?
Are morphisms the same as in T spectra?
So the morphisms are morphisms of T spectra that commute with the structure maps. Absolutely. So you have to take the structure maps into account. And once you have an orthogonal spectrum, now you can define topological cyclic homology for any orthogonal spectrum. So definition, if I'm given an orthogonal cyclotomic spectrum, then you can define Tc of x, the topological cyclic homology of x, by exactly the same formula that I gave you on the very first day of this lecture series, once we had this kind of structure, so that there exists, so given as in the first lecture. So what we do is we have this sort of inclusion map. This is a map they call the Frobenius, which is just going to be going from, the Pn fixed points to the Pn minus 1 fixed points. And then, so that's just as before. There's nothing special or complicated about that. But one thing I was not able to say on Wednesday was where this other map R was coming from. But now that we know the cyclotomic structure, we can say where this map is coming from. So it comes as follows. We're starting in the CPN fixed points. And then we're using the fact that the CPN fixed points is the CPN minus 1 fixed points of the CP fixed points to say that there's a map here into the geometric CP fixed points, CPN minus 1, like this. And then we just use our equivalence. So use our phi, CPN minus 1. So we just use those maps F and R, and we can use exactly the same construction, where we first build this TR construction, and then we take the equalizer of TR with respect to F and with respect to the identity. So once you have a cyclotomic structure, you can define topological cyclic homology. So the last thing I want to say in this brave new algebra context, before getting to the infinity category things, is something about cyclotomic structure on THH. Yep? let's see. So this would be phi CP, phi P. So we have an equivalence from phi CP of x to x that is actually called phi P, not just phi. And then I'm just using the, okay.
What kind of fixed points are they?
Those are actual, honest fixed points. And categorical. Yeah. Let's see. I think in the end, because you're going to be taking homotopy limits and such, that's a good question. There's a subtlety there, but this really are honest fixed points. Okay, so we can't just, as I mentioned briefly once, we can't just take the THH that we would get by looking at the simplicial construction that I gave before and just taking a geometric realization. We need to be a little bit more sophisticated. So we need a replacement for sort of the iterated mass product. So if A is now an algebra in orthogonal spectra, so we have we have a monoidal structure there, as I said yesterday. And so we can talk about algebras in that category. And we could just use the formula that I've repeated 3 times, I think, for Hochschild, where we have the iterated tensor product, and then we use the face maps that are just multiplying and so on. But that's not going to give us what I want. It's not going to be as homotopy invariant as we want. And moreover, we can't really get a cyclotomic structure in that case. So we need a replacement for this to get something that's actually going to be homotopy invariant without requiring that the algebras be cofibrant. And to get the cyclotomic structure. So this is where Bergstedt's original construction comes into play. So he has a natural equivalence between the iterated smash of A and something that we'll just write B of AAA, some sort of construction that he makes that has lots of nice properties that we want to use. It preserves stable equivalences. So it preserves equivalences of orthogonal spectra, and moreover, it has a, I'm not going to explain in too much detail right now because I don't have very much time, but it sort of works nicely together with geometric fixed points. And I'll just say it plays nicely with geometric fixed points. Or let's say with phi of CP, or Cn, let's say, when applied to actually n copies of A. Okay, because of that, we can make the Bergstedt version of the THH construction that will have this B applied to an iterated number of A's in each level. So given an orthogonal ring spectrum, Bergstedt's THH, so his simplicial version of it, the THH of A, let's say, what does it look like in level n? It'll just be this B construction applied to A, n plus 1 copies. And what we get, so we have a term that is equivalent to the iterated smash product, which is what we had before. There are ways of having the face and degeneracy maps that look basically the way they did before, using the multiplication map in A and so on. And this all fits together very nicely. And then you get THH of A, which will be the geometric realization of this construction. And it admits a generalization also to spectrally enriched categories, just as the definition of Hochschild homology in the DG context admits a generalization to DG categories. So let's just, I'll give a list of properties here. So the first and perhaps most important for us is that there's a natural cyclotomic structure on THHA, which really exploits the fact that we built this from this Birkstedt construction rather than just from the iterated smash product. There's a natural trace map that can be defined fairly concretely from the K-theory of A to its THH. Here's one that is dear to my heart because it makes the connection again with free loop spaces, which I think is, it shows that what we were already seeing on the level of DG things also extends to this more spatial or spectral context. So this is due to Birkstedt and Waldhausen, who showed that if you look at, you take a base space, you look at the base loops on that space, you take the suspension spectrum of that, that's going to give you a ring spectrum where the multiplication is coming from the concatenation of the loops. So this is actually an algebra in spectra. We can apply THH to that, which is going to give us another spectrum, a cyclotomic spectrum, in fact. And this is equivalent to the suspension spectrum of the free loop space. So this is a spectral analog of one of the results that I gave to you yesterday. Fourth point is that THH generalizes to categories enriched in orthogonal spectra, so a spectral version of DG categories, and have agreement, which is to say that THH of a ring spectrum A is equivalent to the spectral category of, well, what are often called the category of fixed submodules, but I'll just write it as sort of a perf A. Perf A here meaning the thick subcategory of the category of A modules generated by A itself. So we also have agreement in that sense. And then finally, it also satisfies meridian variance and localization. So it satisfies all kinds of nice properties, generalizing those that have been known for a long time in the classical context. So I'll just write those as words, but they generalize the well-known properties for Hochschild homology in the more classical context. Okay. So now that we have this framework which was set up in Brave New Algebra, we see that these cyclotomic gadgets, they're not too complicated, but there's a fair amount of structure. And in order for THH to have this structure, you need to be really careful about what model you're choosing and things like this. Maybe that's some motivation to try to write things in a very pure, as model independent as possible approach, which says, well, let's reimagine the story. So cyclotomic spectra reimagined. So I don't know if that's actually a direct quote from the paper of Nikolaus and Scholze, and in case one of my graduate students used it to describe what he thought was going on in this Nikolaus-Scholze paper. And so what we're going to have to do is move from the world of actual model categories of spectra to infinity categories. So let me just make one general comment. About how we move between these worlds. So Carlos talked about this in his talks, but let me just remind you a little bit. So as Jacob Lurie showed, there's a functor we'll call N, which is called the homotopy coherent nerve, from simplicial categories to simplicial sets, such that so if I have a simplicial category C here, if the category associated, or a simplicial category associated with each of these is, if this is a Kohn complex, then this homotopy coherent nerve of C is actually a quasi-category, so one of the models for infinity categories. So it's a very specific algorithm for starting with, by SCAT I actually mean a simplicity enriched category. Starting with a simplicity enriched category and moving on to getting a simplicial set that is actually a quasi-category in the case where all of the simplicial mapping spaces are in fact Kohn complexes, which means they're fibrant in the usual model structure on simplicial sets. So this is one way to associate a quasi-category to something like this. And in particular, if M is a simplicial model category. So it's a category that has the structure of a model category, so it has weak equivalences, fibrations, cofibrations. It's also simplicity enriched in a way that's compatible with the model structure. Then what you can do is restrict this category to looking at just the cofibrant and fibrant objects. The nicest objects in this category. In that case, all of your mapping spaces now become Kohn complexes. So this MCF is a subcategory determined by the cofibrant fibrant objects. And then we can take the homotopy coherent nerve of that. That is itself a quasi-category. And it's called the underlying infinity category of the model category. And it's the same thing you would get by applying Dwyer-Kohn localization, which is more what Carlos was talking about in his talks. But so in general, we have a way with the categories we started with to associate a quasi-category to the category in question. So the notation I'm going to use, just for simplification, is for and all of the model categories we were considering before are actually simplicial. So every simplicial model category I'm just going to write N of M for this category. Okay? And one thing that a special case of which was shown by Hinich and which was then generalized by Nikolaus and Scholze. So Hinich, something that is extremely useful, is that if your model category also had a compatible monoidal structure, so it has a monoidal product, and this monoidal product is homotopically meaningful in an appropriate sense, then there's an induced monoidal structure in the infinity category sense on this associated quasi-category. So if M, now I'll say with a tensor product and an identity, is now a symmetric monoidal category, symmetric monoidal model category, then the homotopy coherent nerve of M, or of the cofibrant-fibrant objects, is a symmetric monoidal infinity category. Now, I'm not going to define what a symmetric monoidal infinity category is. That would be a lecture unto itself. But if you don't know what it is, just think about a symmetric monoidal category, and that'll be good enough for today. But just to say that there is a way we can talk about algebras and such in this infinity category context, which is very important for us. So I'm going to give you a dictionary. Sorry? Yeah, so Kahn complex is a fibrant object in simple. So, and the point. So a Kahn complex is fibrant in quasi-categories, but it's because any quasi-category is fibrant. It's correct. Quasi-categories are fibrant in the Joyal structure on simplicial sets, and a Kahn complex is a quasi-category. Okay. So a dictionary. So here are the model categories that I described in the previous section. And on the other side, the corresponding infinity categories. So applying this construction that gets us from model categories to infinity categories. So the first one we had was orthogonal spectra. If we take the associated infinity category, we're just going to call it SP. And it is equivalent to all the other infinity category models for the stable homotopy category. GSP, like this, we'll just take away the O again, because somehow that very specific part of the structure is forgotten when we go to infinity categories. And if we take this category where we're looking at the F equivalences, maybe I'll put the F there, and we're going to write it like this. So those are the associated infinity categories. And there's one more infinity category we're going to look at, which is going to be for spectra with coefficients in the proof ring. So we're going to write CP infinity SP for the limit in the category of, let's say, quasi-categories. So quasi-categories are simplicial sets. We know how to take limits of simplicial sets. It's something that's done level-wise. Of all of these categories, CP and SP. So we build, this is a new one that we didn't have before in the non-infinity context, and that we build now. That's coming. That's the next board. Excellent question. So the functors. All right.
So does that come from the model category for CP, the infinity, SPF that we haven't talked about?
I don't know, and I suspect it doesn't because they don't introduce it on this, but it's a good question. I think it's something that's just easier to define directly in this infinity category world because it's very easy to say what this limit is in infinity categories. Right, so SP is the underlying infinity category of SPO, if you will. But that's what you have in dictionary definitions. So I guess that makes sense. Yes? I'm considering the G stable equivalences as I defined them yesterday. Yeah. OK. So induced functors, what do we have? So there's a functor that I'm going to call U because it's for a forgetful functor. From GSP to, I take the category SP that I define there, and I look at G objects in SP. OK? How are they different? Well, they're quite different, actually, because here this coming from you have very different equivalences that are going on here. The point is, this exists since the forgetful functor here preserves equivalences. Because in particular, it's an equivalence when you take G to be you take the trivial subgroup here. So that induces this functor here. Okay? Now, moreover, because geometric fixed points and preserves equivalences, and because fixed points preserves actually categorical fixed points preserves equivalences between fibrant objects, we have the following, that we also have for every, maybe I'll do this more generally, like this, GSP to SP for all subgroups H of G. So this is clear because this was, I said that this one preserving equivalences, and this one preserves equivalences at least between fibrants, so that's good enough. And in particular, if these guys are actually normal subgroups, then you can consider this as mapping into G mod N SP. Okay? And there's a natural transformation from the categorical fixed points to the geometric fixed points that basically comes from the fact that you can include trivial representation into the regular representation. Finally, we have yet another kind of fixed points. I knew you felt like there was something lacking, right, in this complexity. So there are other kinds of fixed points. So observe that for every H and G, we can consider the following composite. Okay, so we can use this functor U from GSP to SPBG, and we can just take the ordinary limit functor over BG to get into spectra, because this is going to if we look on the level of the model categories, it's preserves equivalences between fibrants, so no problem. So we have an induced functor. And this composite here is called the homotopy fixed points of G. And you can do it for any subgroup H of G as well. And similarly, you have a homotopy orbits functor. Or maybe I should say H in any case. You have a homotopy orbits functor as well for every subgroup H and G. Okay. Moreover, there's a natural transformation between the categorical and the homotopy fixed points. All right, so here I've talked about analogs of these different categories of equivariant spectra. Now what about cyclotomic spectra? So you can say, well, let's just take the underlying infinity category of the category of cyclotomic spectra. But we'd like to sort of, in the end, we'll end up doing something like that. But we'd like to have a better idea, a clearer idea of what we actually get that way. So we're going to kind of construct it by hand. So I'm going to give you two possible answers, and then state the main theorem of the Nicolaus-Schulze paper, which is to say that these two definitions actually give you the same thing, or equivalent things. So in the first case, I'm going to try to sort of generalize what I had already in the brave new algebra case. So what am I going to do? So first I'm going to look for a fixed P. And I'm going to define a P-typical version of the cyclotomic structure. So I'm going to say that what they call the genuine P-typical cyclotomic spectra is the following. I'm going to take an equalizer of the following quasi-categories. So I use this proofer category that I defined up there, SP, right? And there I have the identity. There I have phi p, like this. Sorry, that's the wrong phi. It's capital Phi, so it's geometric fixed points, because we have this induced geometric fixed points functor, which actually extends to the proofer rings as well, like this. Now, here we're using the fact that Cp infinity mod Cp is still isomorphic to Cp infinity, so this diagram makes sense. And we take an equalizer of quasi-categories, so equalizer of these special sets that gives us another quasi-category. And this is what we call the infinity category of genuine p-cyclotomic spectra. So this one is really sort of exploiting the kind of structure that we already had in the cyclotomic case when we're talking about orthogonal spectra. And it's based on the idea that we're trying to put ourselves in a situation where phi c of p is an equivalent. So it's kind of like an identity. That's the motivation for taking this equalizer here, that this should give us something like the p-cyclotomic spectra that we were considering before. So what do the objects here look like? Morally speaking, so the objects in this infinity category, they are actually composed of pairs like this. So it really does look like part of the cyclotomic structure that we had before. OK, and what about the integral case? So we want to put all this primary information together to get an integral picture. So how are we going to do that? Well, one thing to notice is that, observe, if we invert all the F equivalences, which is what happens when we take this localization to get the infinity category, then this gives an action of the positive natural numbers on this category. Okay? Because there we go. And so what you do is you set the integral version of genuine cyclotomic spectra to be what you get by taking the homotopy orbits of this action on this category. Homotopy fixed points, thank you. I wrote the right thing, I said the wrong thing. Homotopy fixed points, absolutely. So what are the objects? Okay, so this is the category of genuine cyclotomic spectra. So let me just write down what the objects here look like morally. So the objects now are pairs of an object in this of a spectrum together with, or T spectrum rather, together with a family phi n, phi cn x, like this. And these guys are T equivariant. Again, using the fact that T mod Cn, just the identity. And this should be some sort of a homotopically coherent, homotopy coherently commutative family. So plus some sort of commutativity conditions that are maybe a little bit technical to express really completely in full detail. And this is one reason why we're going to be interested in the second version of cyclotomic spectra, because it'll enable us to avoid these sort of coherence conditions. Okay. Then it turns out that this category really is the underlying infinity category of the category of cyclotomic spectra. So is means is equivalent to underlying infinity category of cyclotomic spectra. So this is proved by Nikolaus and Scholze. And there's a similar result for a fixed P. So we have a way of understanding now this category. But we'd like to avoid these sort of somewhat messy commutativity conditions, and that's going to be the second approach to thinking about an infinity category of cyclotomic spectra. Okay, so the second approach is Nikolaus-Scholze. Cyclotomic spectra. So in order to define these, I need first to define a generalization of the classical algebraic Tate construction to this context. So definition. Here's the tool that we need. Let's start with G, a finite group. So G be a finite group. And we're going to consider a stable infinity category, so like an infinity category of spectra. Let C be a stable infinite category. So we can just think any of the categories we're thinking about is stable in this context. Admitting all limits and colimits that can be indexed by BG. So that the constructions I want to make actually make sense. Okay. Once we have that situation, then it turns out that there is an analog of the usual norm map, which goes from the homotopy orbits, homotopy G orbits of an object in C to its homotopy fixed points. So we actually have a natural transformation. So this is sort of a definition / proposition, because the actual construction of this norm map requires some effort in the infinity category context. But just think about the ordinary situation with G actions on sets, and it's a motivation in any case. There's a norm map they denote like this, norm G, which is a natural transformation from homotopy fixed points, homotopy orbits, to homotopy fixed points. Okay? All right, once we have that, then we can make the key construction for the definition of Nikolaus-Scholze cyclotomic spectra, which is now an infinity category analog of the usual Tate construction or Tate complex. So the Tate construction is then the function that's given by taking a look at the cofibers or the co-kernels, if you will, of this norm map from homotopy orbits to homotopy fixed points. So it's the functor that will denote like this, Tg from objects in C with an action of G into C itself that takes an object X with its action to the cofiber of the norm map. Okay, so this really entirely deserves its name. For example, if we take C to be our infinity category of spectra, and we take M to be a G module, so a module with a G action or a Z of G action, if you will, and you take H of M to be the corresponding Eilenberg-MacLane spectrum, which is also a construction that lifts to infinity categories, then the ith homotopy group of the Tate construction on M is indeed the Tate cohomology of G with coefficients in M. So this generalizes nicely what we already had in an algebraic context. Okay. So now I can finally, with 10 minutes remaining in these 3 hours, define what these Nikolaus-Schulze's cyclotomic spectra are. Here we go. So if we want to have the infinity category of, all right, Nikolaus-Schulze p-cyclotomic spectra, so what are we going to do? Well, we're going to take first the category of all spectra equipped with an action of the Prüfer group. And we're going to map that into here. By, on the one hand, the identity, and on the other hand, the Tate construction, using as usual the fact that Cp infinity mod Cp is isomorphic to Cp infinity. And here we're going to have a certain fibration, which is given by taking this category and coternsering with delta 1. So you're looking at all paths in there. And this is just evaluation on the endpoints. So if you'd like, we can write that as evaluation on 0, evaluation on 1. So this is actually a diagram in simplicial sets. This is not too intimidating, even though when we call it infinity categories, it might seem that way. When we take the pullback here, this is the category, the infinity category of p-cyclotomic spectra. What do the objects look like? So objects in this case are pairs of a spectrum equipped with an action of Cp infinity, together with a map phi p from X to its Tate construction, which is Cp infinity equivariant. Very simple. And what about the integral case? It's quite similar. So and I look at the infinity category of all cyclotomic spectra of the integral version. Then it's also given by a pullback, which is a little more involved because we want to take all of the primes into account. So how are we going to do that? Well, now we're going to start with a spectrum with a T action. And we're going to map into the product of two copies of that. It's be a similar map here. One component will be the identity. Oh, sorry, this is not what I wanted to do. I need to do a product over primes. Sorry. Do it like this. We take a product over all primes of this category. There we go. Sorry. So what are we going to do? Well, I'm sorry? I'm sorry, what did you say? No, I want BT.
There's no key in the thing you're taking products.
I know. I'm aware of that, yes. Thank you. No, that's on purpose because we really want everything to be T equivariant all along. So what are we doing? So we're actually going to take, so it's an equalizer of, again, something like an identity or a diagonal, I suppose. And then on the other hand, you take the TCP, the Tate construction for CP, over all P, like this. OK. So, and this is more like diagonal, I should really say. OK, iterated diagonal. So I map in there this way. And the reason why it's BT and not CP infinity is because I'm using the fact that T modulo CP is isomorphic to T, yet again. And again, we're going to here have the map over all primes. And again, look at paths in there and evaluate on the endpoints. So what this is doing, if you take a pullback like this, is kind of identifying in each point, up to equivalence, the identity with this Tate construction. So we take the pullback here, and this is our category, our infinity category of cyclotomic spectra. What do the objects look like? The objects look like pairs of a T spectrum together with maps for phi p from x to x TCP over all p, and this thing is T equivariant. That's it. No coherence conditions, nothing like that, just a sequence of maps. You mean up there or down here?
Up there.
Delta 1. So it's like the unit, the interval. OK? All right. So now we have these categories. And let me just give you an example of a cyclotomic spectrum. Crucial example, let's take the sphere spectrum, and let's endow it with a trivial action of the circle group. So I'll call it S triv, sphere spectrum equipped with a trivial action of the circle group. So this is as an object here. And I claim that I can equip this with a cyclotomic structure. How do we do that? Well, it's relatively straightforward because we have S. S always maps, because the action is trivial, and in particular CP action is trivial for every P, there's a map from S into the homotopy fixed points via a map into the fixed points, if you will. So because the action is trivial, we have this map here. And then you have the quotient map down to TCP. And this composite is our phi p. And it turns out you have to do a little bit of work, but not too much, to show this map is actually T equivariant. So it's quite straightforward to get this structure. And this relatively simple-seeming cyclotomic object is actually extremely important. So there's the fundamental comparison theorem, for which I unfortunately don't have time to explain what the functors are, but they're actually not too hard to describe, is that there are equivalences of infinity categories between the categories of genuine cyclotomic spectra, which is the one that is the underlying infinity category of the category of cyclotomic spectra we talked about before. And the Nicolaus-Schulze cyclotomic spectra, and also in the p case. So this is what Nicolaus and Schulze call the main theorem in their paper, that you can act that these categories, which seem much simpler, these infinity categories, are actually equivalent to the underlying infinity categories of the usual categories of orthogonal of cyclotomic spectra. Oh, sorry, whoops. There's a caveat here. When restricted to bounded below spectra. Bounded below means that the homotopy groups are bounded below. Below a certain point, all the homotopy groups are 0. But once you restrict to bounded below spectra, you get an equivalence. Okay. So in the last 2 minutes, let me say something about how we can think about TC in this context. In the context of the Nicolaus-Schulze cyclotomic spectra. Once you have this definition, it turns out to be relatively straightforward. So one remark before I make this definition is that we have mapping. If we have a stable category, so if C is a stable infinity category, so that's any of the examples that we're interested in, then if I have any objects x and y, you actually have a mapping spectrum and not just a mapping space of objects between x and y. So you can always do it like this, which enables us now, that's the mapping spectrum between two objects, to define TC. So for x, a cyclotomic spectrum in the sense of Nicolaus-Schulze, TC of x is just the mapping spectrum in the category of cyclotomic spectra from S triv, which we defined just there, to x. Pretty simple to express. And also for p. And then you can say that since we have this comparison between genuine cyclotomic spectra and Nicolaus-Schulze cyclotomic spectra, we can say, well, what about comparing their TCs? And there's another theorem due to the same guys, which says that if x is a cyclotomic spectrum of the genuine sort, bounded below, then via this functor that I haven't described explicitly, you can see it as a cyclotomic spectrum in the Nicolaus-Schulze sense. And it turns out that its TC in the genuine sense is equivalent to its TC in the Nicolaus-Schulze sense. And the same for p. So what I won't have any time at all to talk about, unfortunately, is the following theorem, which says that if I have any ring spectrum, so if A is at least an E1 algebra in spectra, which you can think of as some sort of associative algebra in spectra, then there's a natural cyclotomic structure on TH of A. So if you have to decide what do you mean by TH of A in this context, you can do the same sort of simplicial construction that I was doing before. So there's a cyclotomic structure on here, and it's natural. In the case when you actually have an infinity algebra, it's a little easier to describe, but you do get this cyclotomic structure, which is well behaved, and so that you can actually talk about the topological cyclic homology of a ring spectrum because its THH has a cyclotomic structure in the sense of Nicolaus and Schulze. And I'm sorry I don't have time to talk about that today. Thank you very much. Uh-huh.
So I'm sort of curious if there's an obvious relation, and also like if you just consider the sum monoid powers of p, does that give you the particular?
I'm the wrong person to ask. One person to ask might be sitting up there in the balcony. I would suspect the answer is probably yes, but I do not know. So ask Lars. And if you'd like to come privately and hear about where the cyclotomic structure on THH comes from, I'd be willing to have a little private lecture at some point, just 15 minutes to do that. So. You have to be a little bit careful about, I mean, so the moral structure is really just like, but you do have to fiddle with it a bit. I mean, doing it for associative algebras is relatively delicate. It's quite a serious combinatorics that goes into it. The infinity case is much, much easier because there's a natural map from a commutative E-infinity ring spectrum into THH of that thing that satisfies a very nice universal property that you can then use to build the cyclotomic structure. You don't have that universal property in the case of just associative algebras, and so you have to get your hands pretty dirty. But it's not the Birkstedt construction.